In the last video, we talked about how we could create a voltaic cell or galvanic cell, or essentially a battery, by separating the oxidation and the reduction reactions and connecting them with a wire, which forces the electrons that zinc is losing to go through the wire to go to copper, to go to the copper ions so that they can get them, so that the copper ions can be reduced. Now that might have raised some questions. If this is a battery, well, what is the positive terminal? What is the negative terminal? If this is a battery, what is the voltage of this battery? Well, I'll encourage you, first of all, when you think about the terminal, what's the positive and what's the negative terminal? I encourage you to pause this video and think about that on your own. Where is the current coming from and where is it going? Well, the negative terminal of a battery is where the electrons are coming from. So the electrons are coming from the zinc bar right over here. So this is the negative electrode of the battery, that right over there. Or the negative electrode is often called the anode. That is the anode of this battery. And on the other side, the copper bar, this is where the electrons are going to. This is the positive. That's the positive electrode, or sometimes called, or what tends to be called, the cathode. Now the next question is, what is the voltage across this? And that voltage is going to depend on what's the concentration of zinc ions you have, the concentration of copper ions you have. It'll depend on the pressure. It'll depend on the temperature. But all of that has been standardized, and you can actually look up standard electrode potentials. And I encourage you, you could do a web search for standard electrode potentials, and you'll see a bunch of voltages for different ions. And it's essentially a measure of relative to hydrogen, and this is all relative to hydrogen. How much does this ion want to grab its electrons? And so if you were to look that up, you would get it for this reaction right over here for the copper ion with an oxidation state with an oxidation number of +2 to grab these two electrons and turn it into solid copper relative to what they call the standard hydrogen electrode. That has a 0.34 voltage, which means that it's more likely to happen than in the case with a standard hydrogen electrode. And don't worry too much about that. We're really just going to compare the voltages and seeing well, what is the total electromotive force, or the total voltage with which this redox reaction is going to happen, or the total electromotive force with which we're going to push these electrons across the wire. If you were to look up the zinc reaction in a table of standard electrode potentials, you might see negative 0.76. Now you have to be careful though, because they're going to give you, if they're giving you this number, they're giving you the opposite reaction here. They're giving you the reaction from going from zinc ions, grabbing some electrons, and becoming solid zinc. We want the other reaction. This is the reaction that we need to occur for our galvanic cell. So this reaction right over here is going to be the negative of that. So it's going to be positive 0.76 volts. So one way to think about it is this wants to happen with an electromotive force, or kind of the energy per coulomb relatively, of 0.76 volts. This wants to happen with the electromotive force here is 0.34 volts. So combined, this entire reaction is going to happen with an electromotive force, or you could say that the potential per coulomb difference between this side and that side is going to be the sum of these two things. And so that's going to be, if we have the standard concentration, which would be one molar, which is 1 mole per liter of the ions in their aqueous solution, if we're at standard temperature, standard pressure, then we would have essentially constructed a 1.1 volt battery, and I've just added these two things together. And of course, there's other ways you could do it. You could literally just take a voltmeter and measure what is the volt without the current there, without the current flowing. You could literally just measure what is the voltage difference between these two terminals, just as you would do in a traditional battery.